Welcome to all. So in our today's class, we are going to see what is moving coil instrument. Moving coil instrument, in that type we are going to see what is permanent magnet type moving coil instrument. So this permanent magnet moving coil instrument is mostly used for voltage and current measurement. This can be used as an ammeter and voltmeter for measuring current and voltage. This is well suited for DC measurement. We will see how it is only suited for DC measurement later, and it is also a very accurate type of instrument for DC measurement. Okay, we will see what is permanent magnet moving coil type instrument. We are going to see moving coil instrument. In that we are going to see permanent magnet moving coil instrument. In short, we can write it as PMMC instrument, permanent magnet moving coil instrument. First we will see the working principle of permanent magnet moving coil type instrument. The working principle is the general motoring principle. The working principle is when a current carrying coil is placed in a magnetic field produced by the permanent magnet, the coil experiences a force and it. So, when a current carrying coil is placed in a magnetic field which is produced by the permanent magnet, what happens is this coil will experience as a force. That force will make the coil to move in the magnetic field. This is the working principle of permanent magnet moving coil type instrument. Why it is called as permanent magnet moving coil type instrument is, here the permanent magnet which is used is permanent or stationary, and the coil is called as moving coil which will be moving in the magnetic field of the permanent magnet. So, we are calling it as permanent magnet moving coil instrument. Next we will see the construction of permanent magnet moving coil type instrument. So, as we have seen the working principle, the same as D'Arsenoval galvanometer principle. Okay. Next we will see the construction. So, in the construction we are having two permanent magnets which surrounds the coil with north and south poles, and we are having a rectangular coil which will be wound on a aluminium frame. Inside that coil there will be a cylindrical core. So, this moving coil will be suspended with the help of a suspension which is held with the help of a jewel bearings. It is supported with the help of a jewel bearings, and we are having a control springs on the bottom and top and bottom of the suspension, and we are having to the same spindle there will be balancing weight. It is used to balance the weight of the instrument. To the same spindle a pointer will be connected. There will be a pointer which moves over the graduated scale, and below that scale there will be a mirror arrangement in order to take accurate readings. So, these are the permanent magnets. This one is the coil and aluminium frame. This one is the iron core. This is the control springs which is used to produce the controlling torque. These are the jewel bearings used to support the spindle. There will be a spindle and there will be a balancing weight which balance the weight of the instrument. The pointer will be attached to the same spindle which moves over the graduator scale, and there will be a mirror which will be placed to mirror the scale in order to take accurate readings. This is the diagram for permanent magnet moving coil type instrument. Now we will see the diagram for the top view of the permanent magnet moving coil instrument. So while looking from the top view, we will be having a spring in the center. So the moving coil will be wound on the, this one is the spring. The moving coil will be wound down the spring on a rectangular frame, and there will be a cylindrical iron core. All this will be, there will be a pointer which will be attached to it, which will move over a graduator scale. Below that we will be having a mirror. So this one is the mirror, scale, pointer, iron core, moving coil, a permanent magnet, spring, and there will be a balancing weight in order to balance the weight of the instrument. I have marked the spring here. This is the top view of permanent magnet moving coil type instrument. One by one we will see the parts of a moving coil type instrument. The first one is moving coil. As we have already seen in the galvanometer construction, the moving coil will be rectangular or circular, and it has number of turns of fine wire which is wound on aluminum former. It's wound on aluminum former that is rectangle in shape, and this moving coil will be pivoted with the help of a jewel bearings, and the coil is suspended so that it freely rotates in the magnetic field of permanent magnet. So the moving coil, this moving coil is rectangular in shape. It is wound on a rectangular aluminum former, and it is pivoted with the help of a jewel bearings, and the coil is suspended so that it freely moves in the magnetic field. The coil is suspended such that it freely moves in the magnetic field produced by this magnet. So the coil frees smoothly inside the air gap between these magnet, that is in the magnetic field of the magnet. The second one is iron core. So the iron core is spherical in shape if the coil is circular in shape. The iron core will be cylindrical if coil is rectangular. So, in our case, in our diagram, the coil is rectangular which is wound on a cylindrical iron core. What is the advantage of this cylindrical iron core? Why are using the cylindrical iron core is? So, the length of the air gap across which the magnetic flux has to pass through is reduced, and the flux, so what happens is the flux linking the coil is increased, which increases the deflection torque Td. Which in turn increases the sensitivity of the instrument. So, the advantage of cylindrical iron core is the length of the air gap across which the magnetic flux has to pass through is decreased. So, the flux linking with the coil increases, which increases the deflection of the coil, which in turn increases the sensitivity of the instrument. Practically, the flux between the core and the poles of permanent magnet is always radial. So, the magnetic field produced by the flux produced by the permanent coil will be radial. So, in radial field we know that the deflection produced by the coil will be directly proportional to the amount of current flowing through the coil. So, in case of permanent magnet moving coil instruments, the scale will be uniform. This is the advantage of using cylindrical core and permanent magnet. Third one is permanent magnet. It produces the necessary magnetic field, produces the necessary magnetic field. So, the magnetic field produced will be uniform, radial and horizontal. We have seen what is the importance of radial magnetic field, which increases the sensitivity of the coil. And the fourth one is spring. You know that the spring will produce the controlling torque, used to produce the controlling torque Tc. So, we have two phosphor bronze hairsprings which is used to produce the controlling torque. It also carries current in and out of the coil. The spring also carries the current which is to be measured. And the fifth one is spindle. So, from the diagram we have seen that to the spindle the moving coil, pointer and the spring is attached. So, when the spindle moves or when the moving coil moves, along with the spindle the pointer and the spring is also moves. The next one is the pointer, which is light in weight and moves over the graduated scale to measure the amount of current flowing through the coil. Measure, that is, measure means it will indicate the amount of current flowing through the coil. Next one is balancing weight. So, balancing weight is used to counterbalance the weight of the instrument. So, these are all the parts in a moving coil type instrument. Next we will see the working of moving coil type instrument. Now, we will see the working of moving coil type instrument. Before seeing the working, we will look into the diagram. So, here we will see the working of a moving coil type instrument. So when the magnetic field is produced by the radial magnetic field is produced by the permanent magnet, right? So when the current flows through this moving coil, what happens? The current carrying coil will be placed in the magnetic field produced by this magnet. So it will experience a force according to the working principle. Now what happens is this moving coil will move inside this magnetic field. So when a current carrying coil is placed in a magnetic field, will experiences a force and moves inside this magnetic field. Okay. So due to the magnetic effect of the voltage or current, an electromagnetic field is produced so that this coil experiences a force. So we know that this coil is connected to the spindle. So when the coil moves, along with that coil, the spindle also moves. Also we know that along the spindle, the control springs and pointer are connected. So when the spindle moves, the pointer connected with the spindle also moves over this graduator scale, and the spring will experience as a force, and will, because of that force, what happens is the controlling torque will be produced, so that the controlling torque will oppose the deflection torque produced by this coil, so that the pointer will rest at a equilibrium position. Now this controlling torque will make the pointer to rest at a finite magnitude, so that the pointer will shows the amount of current flowing through the coil. So in order to make the pointer to rest at the position very quickly without any oscillations, we need damping torque. So that damping torque will be produced by eddy current damping. We will see what is eddy current damping. So this damping torque here will be produced by the eddy current. Let us see how this eddy current is produced. This eddy current is produced in the aluminium former on which the moving coil is wound. So the aluminium former on which the moving coil is wound, there will be a eddy current. Let us see how the eddy current is produced in this aluminium former. This aluminium former is a non-magnetic material over which the coil is wound. This is a rectangular aluminium coil over which the coil will be wound, which moves in the magnetic field. There will be a magnetic field produced by this permanent magnet. So this coil will move in the magnetic field of the coil when current flows through the coil. When the coil moves, the frame on which the coil is wound, that is this aluminium frame, also moves along with that coil, which will be connected to a spindle, right. So this aluminium former acts as a conductor. We know that when a conductor cuts the flux, an EMF will be induced in this conductor. Now the aluminium former acts as a conductor which moves in the field produced by this magnet. So what happens is, this conductor will cut the flux produced by this permanent magnet, so that an EMF will be induced in this aluminium former. We know that when a conductor cuts the flux, an EMF will be induced in the former. When a conductor cuts the flux, EMF will be induced in the former. Because of that EMF induced inside this conductor, what happens is a small current will flow in this closed path of the aluminium former. That small current is called as eddy current. So this eddy current produces a force or torque which opposes the moving coil. This is as per Lenz's law. So as per Lenz's law, we know that the eddy current will produce the force which opposes the cause producing it. The cause for the production of eddy current is the movement of moving coil. So, the eddy current will produce a torque or force which opposes the movement of the moving coil as per Lenz's law. So, what happens? It produces a torque. That torque is called as damping torque. What this damping torque do is, this damping torque will damp the oscillations of the pointer. Oscillations of the pointer and brings the pointer to rest quickly so as to reduce the time consumed for taking final readings. So, the damping torque will damp the oscillations of the pointer so that the pointer will rest quickly at a steady state position. So, the time taken for the taking readings will be reduced with the help of this damping torque. So, this damping torque is produced by eddy current damping in case of permanent magnet moving coil type instrument. Already we have seen in moving iron type instrument how the controlling torque is produced. How the controlling torque is produced? It is produced with the help of the springs. The springs, we are having two springs attached to both ends of the spindle, that is one end of the spring will be connected to the spindle and other end of the spring will be connected to a lever arrangement. There will be a lever arrangement which is activated by a screw which is placed on the in front of the meter. So, by adjusting that screw we can adjust the zero position of the meter. So, this spring will used to produce the controlling torque. What is the necessity for controlling torque? Necessity for controlling torque is, it brings the pointer to zero position when deflection of the moving coil is removed. How the deflection of the moving coil is removed? If we disconnect the current which passes through the moving coil, what happens? The deflection torque produced by this moving coil will be 0. So, the pointer comes to the 0 position with the help of this controlling torque. If there is no controlling torque means, the pointer will never come back to zero position. It's the necessity for controlling torque. Next we will see the torque equation of permanent magnet moving coil type instrument. So, equation for the torque of permanent magnet moving coil type instrument is derived from the law of electromagnetic torque, from the law of electromagnetic induction. The deflection torque produced in moving coil type instrument is equal to NBA into I. Let us take this equation as equation 1, where N is the number of turns in the coil, B is the flux density in the instrument, flux density of the coil between the air gap which is taken in Weber per meter square. The number of turns is taken as 10 meter, and A is the effective area of the coil in meter square, and I is the current in moving coil in amperes. So, the deflection tag TD can be written as G into I, where G is equal to NBA, which is taken as constant. Next we will know, let's take this equation number 2. We know that the controlling torque TC is equal to K into theta. So, take this equation as equation number 3. So, at final steady state position, we know that the deflection torque produced will be equal to the controlling torque. So, substituting 2 and 3, we will get Gi equal to K into theta. Theta is equal to Gi by K, that is G and K are constant, theta equal to G by K into I, or we can find the value of current I is equal to K by G into theta. So, from let us take this as 4th and 5th equation. So, from 4 and 5 we can say that the deflection produced by the moving coil will be directly proportional to the amount of current flowing through the coil. So, in moving coil type instrument, the deflection produced by the coil will be directly proportional to the amount of current flowing through the coil. So, here since the deflection is directly proportional to the current, when the direction of current changes, the pointer deflection also changes, and it will come to rest at a 0 position, which the torque will be 0. So, this is used for, it is permanent moving coil type instrument is used only for DC measurement, and it cannot be used for AC measurement. Let us see the advantages of permanent magnet moving coil type instrument. So, we are having uniform scale in permanent magnet moving coil type instrument. Since we are using permanent magnet and eddy current damping is used, we are having a uniform scale because the deflection torque is produced which is proportional to the deflection of the pointer, which is proportional to the amount of current flowing through the coil, and low power consumption, that is the power consumed will be in the order of 25 microwatt to 200 microwatt, and high accuracy, and it also sensitive, highly sensitive and accurate. It is not affected by external fields. Since we are using permanent magnet not to produce the necessary magnetic field, it will not be affected by external field like moving iron instruments. Next we will see the disadvantages. Since the deflection is proportional to the current as derived from the torque equation, it is used only for DC measurement. So, it cannot measure AC and the aging of springs and permanent magnet will causes error. So, this is an advantage, and the cost of permanent magnet moving coil instrument is high. Since we are using permanent magnet and there is a delicate construction, and for accurate machining the cost required to manufacture permanent magnet moving coil type instrument is high. Next we will see the applications of permanent magnet moving coil type instruments. This permanent magnet moving coil type instrument is used for DC measurement. So, you can measure DC voltage or DC current. So, this meter can be used as a DC voltmeter, that is permanent magnet type moving coil DC voltmeter and DC ammeter. This type of meter is used for DC voltmeters and DC ammeters. First we will see DC ammeter. So, microammeters and milliammeters up to 20 milliamps, the entire current will pass through the coil and the spring will carry the coil. Up to 20 milliamps in microammeters and milliammeters. For higher currents, so this moving coil instruments should be shunted by sufficient resistances. So, the shunt resistance must be connected to the moving coil instrument for measuring higher currents. The shunt may be internally or externally connected. So, internal shunt can be used for meters up to 2000 amps and external shunt is used for measuring currents up to 5000 amps. So, in order to make the moving coil meter to work it as a DC ammeter, this one is the basic meter. You have to connect an external shunt resistance for measuring higher values of current. Shunt resistance is mentioned as RSH. So, the input voltage, the total current flowing to this circuit is taken as I, the current flowing through this shunt resistance taken as ISH, and current flowing through meter is taken as IM, and there will be internal resistance of the meter which is taken as R. So, this is the basic PMMC meter. So, for measuring current, the meter should be connected in series with the circuit where its current is to be measured. You all know that the ammeter should be connected in series with the circuit where the current is to be measured. So, from the diagram we know that the total current I is equal to the shunt current plus the meter current. Take this equation number 1. As the shunt resistance and meter resistance are parallel, you can write the voltage drop as ISH into RSH is equal to IM into RM. that is drop across voltage across the shunt resistance and the meter. So from this RSH is equal to Im Rm divided by ISH. This takes this equation number 2. So from equation 1, ISH is equal to I minus Im. So substitute, take this equation number 3. So substitute 3 in 2, will get RSH is equal to Im Rm divided by I minus Im. So dividing by Im on both numerator and denominator will get RSH is equal to Rm divided by I minus Im minus 1. So Rm is equal to M minus 1, where M is equal to I minus Im. It is called as multiplying factor of shunt resistance. It is the multiplying factor for shunt resistance. Let us take this equation as equation number 4. So from 4, the multiplying resistance M is equal to I by Im, which is equal to Rm divided by RSH plus 1. From 4th equation, M is equal to Rm divided by RSH plus 1. So the shunt resistance RSH is the constant temperature resistance via within the case of the instrument. So the shunt resistance will be placed within the case of the instrument, or it is external shunt having a low resistance. Okay. So if we want to increase the range of the meter, to increase the range of a meter by M times the shunt resistance, from this equation the shunt resistance should be increased 1 by M minus 1 times the basic meter resistance, that is Rm. The shunt resistance must be increased 1 by M minus 1 times the basic meter resistance in order to increase the range of the ammeter. So we can increase the range by connecting external shunts. Next we will see the DC voltmeter. We always know that always the DC voltmeter will be connected in parallel across a circuit where voltage is to be measured. So voltmeter, we are having a series resistance which is connected to the basic PMMC meter in order to make it to measure the voltage. So the series resistance is taken as Rs, the meter resistance is Rm. This is the basic PMMC meter. So connecting a series resistance of high value to the basic PMMC meter, we will get a DC voltmeter. So the I is the current flowing through the total current flowing through the circuit, and Im, which is equal to I, will be the current flowing through the basic PMMC meter. So the use of series resistance are, what Rs does is it limits the amount of current flowing through the flowing into the meter. It limits the amount of current flowing through the meter. So the current Im, that is meter current Im, does not exceed the full scale deflection. So, the meter current will not exceed the full scale deflection of the meter. So, I will write the voltage equation. The input voltage is V. So, from the circuit the voltage V will be equal to Im into Rs plus Rm. So, removing the bracket, V is equal to Im Rs plus Im into Rm. Rearranging this equation, Im Rs is equal to Va minus Im Rm. The series resistance Rs will be equal to V minus Im Rm divided by Im, else V by Im minus Rm. So, value of series resistance which is to be compared to the basic PMC meter. You know that multiplying factor for shunt resistance is, which is represented as M, is V by V. So, V is the full scale voltage, small v is the drop across basic meter. So, the full range voltage and the drop across the basic meter, the ratio of full range voltage and drop across the basic meter is the multiplying factor for the series resistance. So, the multiplying factor M can be written as Im Rm plus Rs divided by Im Rm. This is the full range voltage and the drop across the meter is current flowing through the meter and the meter resistance. So, M equal to 1 plus Rs divided by Rm, which implies Rs is equal to M minus 1 into Rm. So, in order to increase the range of voltmeter, M times the series resistance needed is M minus 1 times the basic meter resistance Rm. So, the series resistance needed is M minus 1 times the meter resistance in order to increase the range of the voltmeter by M times. Next, we will see the errors in PMMC instrument. First one is the frictional errors. So, the frictional error will be caused in the permanent magnet moving coil type instrument. This friction error can be eliminated when torque to weight ratio of instrument is made small. When we reduce the value of torque to weight can be eliminated when the torque to weight ratio of the instrument is made very high. The frictional error can be eliminated. Second one is due to temperature an error is produced. So, due to temperature what happens is the resistance of the coil varies for every increase in degree Celsius increase in temperature. The resistance of the coil varies for every degree Celsius increase in temperature. How we can eliminate this temperature error is in case of voltmeters, large series resistance Rs of low temperature coefficient is used so that the resistance of the coil will not vary because of change in the temperature. Next one is aging of the permanent magnet and springs. So, because of the aging of permanent magnet and springs, the error will be occurring in the instrument. So, what happens if the permanent magnet is weakened is it causes less deflection of the pointer when the current flows through the coil. Because of the aging of the permanent magnet, it causes very less deflection, so that accurate reading cannot be noted. And because of the aging of the spring, what happens is it causes large deflection. So, the deflection of the torque will not be controlled by the spring because of the aging of the spring, because the spring produces the controlling torque which causes the pointer to settle in a steady state position. So, the deflection is controlled by the spring. So, if due to the aging of the spring will cause large deflection. So, this can be eliminated by frequently replacing the springs and the permanent magnet. Thank you.